Hello, and welcome back to the Unity Foundations tutorial. Today we'll take a look at scenes and scriptable objects. We'll cover scene loading and unloading, modular construction using multiple scenes, extending Unity's scriptable object class, and cross-scene dependencies and communication. Let's get started. Right now I have my blue cube sample scene loaded. It contains the boilerplate camera, light, and volume objects, as well as a cube created via GameObject, 3D Cube, which I have assigned a blue material, which I created via Create Material. I attached a rigid body component to the cube so that it will enable physics collisions, and disabled gravity so that it doesn't fall off the screen at runtime. I also have a red cube sample scene with the boilerplate objects, and a cube which has been assigned a red material, as well as the rigid body with gravity disabled. We can load multiple scenes at once into the Unity editor by dragging and dropping any scenes we want to load into the hierarchy panel. And we can unload or remove scenes via the scene's context menu and the unload or remove scene options. Remember that the game world is a shared space, so even though your scenes and scene objects can be loaded separately, once loaded, everything exists together, and objects in different scenes can interact. Separating out specific functionality by scene can be useful for modularizing your game systems. For instance, you could develop the player and player movement system in its own scene, and the level content or the system that procedurally generates your level in a different scene. Then you can combine these two scenes together in the editor to test the full experience. Combining the content of your scenes can be done in a few different ways, and the best way for you will depend on the exact requirements of your game. One option is to use a separate master scene that will contain all of the elements that you developed independently. So I'm going to drag my master scene into the hierarchy. You can see it only contains the camera, light, and volume, but no cube objects. We don't want to just copy and paste the game objects from each developed scene into the master scene because it's easy to make mistakes, creates extra work, and doesn't take advantage of the fact that we developed each scene as its own module. Instead, we can use prefabs. A prefab turns a game object into a project asset and acts as a sort of blueprint for recreating instances of that particular game object, similar to how we can create multiple instances of a class. I've created a prefabs folder to help me organize my assets. If I drag and drop the red cube game object into the prefabs folder and the blue cube game object into the prefabs folder, you'll see it creates a new prefab asset for each. You can see the game object icons and names in the hierarchy have turned blue, indicating that these are instances of a prefab. If I drag the prefab into the master scenes hierarchy, it places it at the transform position specified on the prefab. You can see if I unload the blue cube sample scene, the blue cube is still visible in the master scene. I can add my red cube prefab to my master scene also and unload the red cube scene. When I play my master scene, I'll have the same functionality as when I loaded my two scenes separately. The prefabs live outside of any single scene and can be referenced from anywhere in your project. By double-clicking a prefab, you're accessing the master object. Changes that you make to this object are carried over to all instances of that prefab. You can see if I load my blue cube scene again and unload the master scene, the prefab instance in the original scene has also updated to match the master instance. Each instance of a prefab can override the values assigned from the prefab asset. You can see if I drag a second instance of blue cube into the scene view and I change the scale value on this second instance, the original instance and the master prefab continue to keep the same value. After selecting this, if I choose the overrides dropdown, I can choose to apply all of my overrides from this instance to the master instance, and therefore update all instances of that prefab across all scenes. So if you take this approach, just be mindful of where you are making edits and which edits should be applied back to the master prefab. Another approach is to load both scenes simultaneously at runtime, so that the way our game appears when we combine them manually in the editor is the same as how they will appear when combined programmatically in a final application. There is one major difference between playing your game in the Unity editor and playing your game as a standalone executable. The Unity editor can load all active scenes into the temporary runtime environment. But when we publish our game from Unity, we are required to define a single scene that will be loaded when the game starts. If we go to File, Build Profiles, and select the scene list, you can see the list of scenes that will be bundled with your final application. Only the scenes in this list will be able to be loaded, and only the first scene in the list will be loaded at application startup. This means that in order to load both of our modular game scenes, we'll need a third scene to act as the manager. This third scene is the one that is loaded at application start and is responsible for loading the other scenes. To add scenes to our scene list, you can load them into the editor and then use the Add Open Scenes button, or you can drag and drop your scenes from the project assets into the scene list. You can then drag and drop internally to reorder that list. I'm going to place our master scene at index 0. If I jump back to our master scene, I removed everything except for a single game object called SceneLoader, which has a single component on it called SceneLoader. This is a custom mono behavior that I've written. If we look at the mono behavior, you'll see that in the awake method, I'm calling Unity's built-in SceneManager and asking it to load scene at index 1 with the load scene mode additive, and then load scene at index 2, also with load scene mode additive. Load scene mode additive makes sure that the SceneManager doesn't replace existing scenes, but combines them. And if we look back at our build index, you'll see that we have blue cube at index 1 and the red cube scene at index 2. When we run this, we will see that master scene runs its awake method and loads both of our sample scenes. And we get the functionality as before, where these scene objects are capable of interacting. When looking at multiple scenes loaded into edit mode, we're able to see how these scenes look together in the scene view, regardless of the cameras involved. However, because the game view is directly tied to camera output of our scenes, we must be mindful of handling competing cameras. You can see if I change the X position on the red cube scene camera, the game view updates. If I disable the red cube scene camera, the game view reverts to the scene as being rendered through the main camera in the blue cube scene. Occasionally, you might want multiple cameras from different scenes rendering to different viewport areas of the display, such as with multiplayer split screen or an RTS minimap. Or you may need to toggle between cameras based on user input, such as with first and third person perspectives in a racing game. For a standard setup, where we have one camera in each scene module, which is needed during the development of that module, and one of those cameras is the one that we want to render through when the scenes are run together, we can write a mono behavior to handle disabling the unused cameras when more than one is present. I've written a camera manager script that is designed to be placed alongside each camera, as denoted by the require component attribute. It exposes a Boolean field named isPrimary for each instance and a static camera field for tracking the primary camera reference across all instances. When our awake method is run, we get the camera component on this game object. If there is no camera currently assigned as the primary camera, then we assign this camera. If there is already a camera assigned as the primary camera, we check whether or not this camera should be the primary camera. If it should, then we deactivate the current reference and we assign this camera as the primary. Otherwise, we deactivate this camera's game object. The way this script is structured, if multiple cameras have the isPrimary bool set to true, the last one to run its awake method is the one which will take over the render. If we need something more robust, we could write a custom script that exposes a priority integer field for each camera, and that always enables the camera with the highest priority. Looking back at our Unity scene, if we imagine that the blue cube scene is our player, and the red cube scene is our level, we would want to always default to the player camera if the player is present. So you can see I've added the camera manager script to the main camera in our player scene and denoted it as isPrimary. I've also added the camera manager to the level scene, but denoted the camera as not primary. When we run these two scenes together, you will see that the player camera, the blue cube camera, remains active and the level scene camera is disabled. If we unload the player scene such that we were only working on level development, when we run this alone, the level camera is still active, even though it's not denoted as primary. Final use case for modular scene composition is separating gameplay from the UI. Here, I have a new scene with a canvas element. The canvas element is using a screen space overlay render mode and has one Text Mesh Pro text field to display the current number of player lives. We'll use scriptable objects to communicate changes to the game state across these scenes, while also allowing for each scene to be run and tested independently. Next, let's look at scriptable objects. Unlike mono behaviors, where each instance lives as a component on a game object, scriptable object instances are project-level assets. They exist independently of our scenes and can be referenced from anywhere in our project. To create a custom scriptable object class, we extend Unity's base scriptable object class and then add the Create Asset menu attribute. The attribute has parameters for file name, menu name, and order. File name specifies the default file name given to newly created instances of this scriptable object. Menu name identifies the location of the menu option for creating a new instance of this scriptable object. And order can be used to refine the order in the create menu structure. I'm using a value of -1000 so that it shows up at the top of my menu. To create a new scriptable object instance, we can right-click in our project panel, go to the Create menu, and then we'll find at the top, because I used that -1000 order, we have the My menu, My submenu, My first scriptable object, as defined by our menu name. To demonstrate how scriptable objects can be referenced across scenes, I've created a GameState scriptable object class with a single integer value, numLives. I've also created a gameplay script, which holds a reference to a GameState instance and has a loseLife method, which is exposed via the context menu and subtracts 1 from the numLives of the GameState. I've also created a UI overlay script, which holds a reference to a GameState and a text field. In the update method, which runs on every frame, we set the value in the text field to display the numLives value of our GameState instance. Looking back at our Unity instance, I've created an instance of the GameState scriptable object and set the numLives value on that instance to 3. I've also added a gameplay game object with the gameplay script, which is referencing that GameState instance, and a UI overlay object in the UI scene, which is also referencing that same GameState instance. When we run the application, we can see that the UI updates to show the numLives value on our GameState instance of 3. When we access the loseLife method through the gameplay context menu, the shared GameState instance value is updated and the UI overlay displays the new value appropriately. It's important to note that because scriptable object instances exist outside of runtime, changes made to the object will persist, even after exiting play mode. As a result, our shared game state, which started with a value of 3, now holds a value of 1, even after returning to edit mode. In order to maintain the correct starting value on our GameState scriptable object instance, we have a few options, such as initializing the numLives value on the GameState to a starting value in the awake method, or creating a copy of the GameState to hold the initial value and then reassigning that value back to the project asset in the onDestroy method. Because scriptable objects are also ideal for creating configurations to be ingested at runtime, we can combine using a scriptable object config and a scriptable object GameState to prevent accidentally altering our project assets while also increasing our modularity. In this approach, we have a new scriptable object class called GameplayConfig with a single field, starting lives. Our gameplay behavior now holds a reference to an instance of the GameplayConfig, and at awake, it creates a new runtime instance of our GameState scriptable object. Because the GameState instance is being created programmatically at runtime instead of as a project asset via the Create menu, the instance exists only in the runtime environment, and so we don't have to worry about affecting any project assets. We assign the numLives field on the GameState from the value stored in the config. The loseLife method updates the numLives value on the GameState the same as before, but this time it passes the GameState to a static method on the GameState class called reportUpdate. The reportUpdate method invokes a static event called valueChange and emits this event using the GameState instance that was provided as an argument. The UI overlay no longer requires a reference to a particular GameState. Instead, it listens for the GameState.valueChange event, and when it receives it, it updates the text on the text field with the value of the GameState passed with the event. Looking back at our Unity project, I have created a GameplayConfig instance with a starting lives value of 3, and have assigned the GameplayConfig field on our gameplay script to that instance. When we run the project, the gameplay script creates the temporary runtime instance of the GameState and populates it with the starting value from the config. The start method requests the GameState reportUpdate method and passes along the newly created GameState instance. The reportUpdate method invokes its valueChange event and emits the GameState, and the UI overlay updates the value accordingly. As an additional bonus, because the GameState is still a scriptable object, we are able to create instances in our project to use as test assets. I have added a new method to the GameState called testValueChange and exposed it via the context menu. This method invokes the GameState.reportUpdate method, the same method invoked by the gameplay, but uses the project asset as the argument to be passed with the event data. This means that if we unload the gameplay scene and run only the UI scene, we're still able to test the UI functionality through the test GameState asset by setting a number of lives and using the context menu to test the valueChange event, which, as you can see, updates the number of lives in the UI. One final benefit of combining modularized systems with scriptable objects is it makes it easier to maintain and test your project. If we keep our scenes dedicated to serving the gameplay, we don't have to worry about manually turning on and off certain game objects in the scene just to achieve a particular functionality. I've added a new enemy definition class and a list of enemy definitions to our gameplay config. In our project assets, I created 2 instances of our gameplay config to represent easy and hard modes. The configs have different values for the number of starting lives and different stats for the enemies generated by the gameplay. We can provide the scene with these different configurations, which allows us to create and test different gameplay. As you can see, it's extremely useful to be able to create and modify instances of a C# class outside of runtime. For our game state, I've added a user data class, which has a rank and a username. Normally, this information wouldn't go in the game state. It's just here to illustrate how, in our Unity project, I could create different instances to represent different users at different stages in the progression of the game, and use these instances for testing without having the test data polluting our scenes or our final project. Congratulations on completing this episode of the Unity Foundations tutorial. Understanding your options for modularizing your gameplay systems and managing data dependencies between systems are high-level concepts. I hope you find them useful, and if you have any questions, please reach out in the comments. In the next video, we'll cover the canvas system and rect transform components and animations. For more practice working with prefabs, scene flows, and data persistence, check out the Unity Learning Pathways linked in the description.